In today's lecture, we're just going to talk about one last problem to finish up Chapter D. We're going to talk about numerical partitions into unequal parts. Here's our main definition. We're going to define this new quantity, which we'll call P star of m and n. That will be the number of ways to write the number m as a sum of n distinct positive integers. I'll give you an example here with m equals 13 and n equals 4. How can we write 13 as a sum of 4 distinct integers? Well, again, because order doesn't matter, we'll just choose to always write these from smallest to largest. It'll make it much easier to organize things so that we don't miss any. If we want to write 13 as a sum of 4 integers, we could take 1 plus 2 plus 3. These are all distinct integers. That's 6, so we have to add 7. That's one way to write it. But there are other ways to write it. We could write 1 plus 2 plus 4, and then we only need 6. Or we could do 1 plus 2 plus 5, but then we would need 5 there, and those are not different from each other. So these are actually all the ways to do it, starting with a 1 and a 2. We'd start 1 plus 3, plus then we would have to go up to 4, and then we would have to go up to at least 5. And that actually works. 1 plus 3 plus 4 plus 5. That's the only way to start with the 1 and the 3, because if we increased any of these, we would be too big. Can we start with a 1 plus a 4? Then we need to have at least a 5 and a 6, and that would be too big. So these are in fact all the ways to write 13 as a sum of 4 integers if we start with a 1. What if we start with a 2? We could have 2 plus 3 plus 4 plus, well, we already have 9. We'd need 4 more. That's actually not even allowed anymore. So starting with a 2 means we're forced to get too big if we use distinct integers. So these are the only 3 ways to do it. And we say P13, 4 is equal to 3. 3 ways to do it. Our goal is to find a general way to compute P star mn for different values of m and n. And of course, we could start the problem entirely from scratch, but what we would like best is to reduce the problem to a previously solved problem. In order to show how to do that, we'll compute something slightly different. We'll try to compute P star of 13, 3. Remember, we already computed P star of 13, 4. That was only 3. But here, if we write down all the different ways of writing 13 as a sum of 3 distinct integers, we can start with 1, 2, and 10, or 1, 3, and 9, 1, 4, and 8, 1, 5, and 7. We couldn't do a 1, 6, and 6, because those two are not distinct. So then we could start with a 2. And we could have 2 plus 3 plus 8, 2 plus 4 plus 7, 2 plus 5 plus 6. And that's all the ways of starting with a 2. Can we start with a 3? Well, yes, we could have 3 plus 4, and then we need a 6. If we started 3 plus 5, we would have to, it would get us to be too big. So just by an exhaustive search, we've listed 8 ways of writing 13 as a sum of 3 integers, which are all distinct. Now, in order to see what's interesting about these 8, I want to create a transformation, a one-to-one correspondence. This will be in the end, a one-to-one correspondence. Notice that since these integers have to be distinct, I can do the following thing. Leave the first one alone. I can subtract 1 from the second one. I can subtract 2 from the third one. Now you might ask why I'm doing that. Well, the first integer always has to be at least 1. Because they're distinct, the second integer has to be at least a 2. You can never have less than a 2 in that second position. The third integer has to be at least a 3. And since the second one has to be at least a 2, I can subtract 1 from it, and it's still at least a 1. Here we see it's a 1. The third integer has to be at least a 3. When I subtract 2, it has to be at least a 1 still. Now I've subtracted nothing from the first, 1 from the second, and 2 from the third. I've subtracted 3 total, so of course it shouldn't surprise you that the total drops by 3. we get 10 equals 1 plus 1 plus 8. If I do that with that same procedure with each and every one of these ways to write 13, I'll show you what we get. I would get 10 now because I'm going to subtract 1 from the second integer and 2 from the third. I get 10 equals 1 plus 2 plus 7. 10 equals 1 plus 3 plus 6. 10 equals 1 plus 4 plus 5. And then I go to the next ones here. I get 10 equals, what is it? 2 plus 2 plus 6. 10 equals 2 plus 3 plus 5. 10 equals 2 plus 4 plus 4. And finally, 10 equals 3 plus 3 plus 4. I claim at the end of this process, I have every way of writing 10 as a sum of 3 positive integers. In other words, there are 8 ways to do it. I claim that I've counted that P10(3) equals 8. Why is that? Well, if we take any way of writing 13 as a sum of 3 integers which are all distinct, when I apply this procedure of subtracting 0 from the first, 1 from the second, and 2 from the third, I get a way of writing 10 as the sum of 3 positive integers. If I go backwards, if I have any way of writing 10 as the sum of any 3 positive integers, and I arrange them, as we've said before, in order from smallest to largest, I add 0 to the first, 1 to the second, and 2 to the third, I claim that's adding 3 total. We'll get a way of writing 13 now. Still is a sum of 3 integers, and I claim they'll all be distinct now. Why? Well, you notice some of these have terms which are not distinct, but by adding 0 to the first and 1 to the second, that changes them to be distinct. Here again, these were not distinct, these were not distinct. I'm adding 0 to the first, 1 to the second, 2 to the third. I have to have distinct integers because I'm adding bigger and bigger things to larger and larger entries already. There's no way I can create any 2 that are equal, and if I had any 2 that are equal to begin with, they'll become unequal. So if I had any other way of writing 10 as a sum of 3 integers, adding 0 to the first, 1 to the second, 2 to the third would bring me in the other direction to a way of writing 13 as a sum of 3 distinct integers. We've counted carefully all the ways of writing 13 here as a sum of 3 distinct integers. So here we have all the ways of writing 10 as a sum of 3 positive integers. So these two are the same. There's a one-to-one correspondence between these 2 ways of doing things. And that tells me P star 13(3) really should be the same as P of 10(3). They're both 8, of course. Can we generalize this? How can we find a formula for P star Mn? Well, if we write M as a sum of n positive parts, and here I mean, I should have said distinct positive parts. If I subtract 0 from the first, 1 from the second, 2 from the third, 3 from the fourth, 4 from the fifth, all the way up to n minus 1 from the nth, what do I get? I get a way to write some smaller integer, which I'll put down in a second, as a sum of n parts. Now, what smaller integer do I get? Well, how many have I subtracted? When I do this procedure, I subtract 0 from the first, 1 from the second, 2 from the third, all the way up to n minus 1 from the nth. And we know how to add these together. That's just n times n minus 1 over 2. That's the sum from 0 up to n minus 1 of each integer, sum of I from I equals 0 to n minus 1. And there's a next way to write n times n minus 1 over 2. It's not immediately important here, but that just happens to be exactly the same as n choose 2. So since I'm subtracting that much, once I take those all away, I'm going to write not the number m, but m minus n choose 2 as a sum of n parts. because they were written in order to begin with, all of these parts will be positive. And that gives us our result that says P star Mn, the number of ways of writing M as the sum of n distinct parts, is just P of this new number, M minus n choose 2, comma n, the number of ways of writing this new number as the sum of n positive parts.